Hello, warrior chemists. This is Miss Lemons, and today we're going to be talking about the concept behind calorimetry. So, let me move my little face here out of the way. There we go. So let's talk about the law of conservation of energy. Remember, that's the idea that energy cannot be created or destroyed, only transferred. In the previous video, where I talked about the law of conservation of energy, or logo E, we used this example on the left-hand side. Here we have a block of iron that is being heated up by a fire. The fire is transferring its heat energy into the block of iron, which is absorbing that heat energy. The water is also showing a transfer of heat because it's being cooled down. The ice is absorbing the heat energy from the water, and the water is releasing that heat energy to the ice. Notice that there is no creation or destruction of energy. They don't just disappear or reappear. They actually are being moved around or transferred. You can even see that in the block of iron. Some of those pieces of energy or bits of energy are being released into the surrounding air. That would make sense because eventually, if that iron is not heated any longer, it's going to cool down. So all of its heat energy has been released into the environment. But what if we took a heated block of iron and we placed it inside the cooled down water? What do you suppose would happen? Well, if we took that iron and we placed it inside the water, we know that the heat energy of the iron would be transferred or released to the water. The water would then absorb that heat energy, and it would increase in temperature. This is essentially what we do in calorimetry. So, if we place the hot block of iron into the water, the heat energy from the iron will be released and transferred into the water, which absorbs that heat energy. We represent this using the following equation. Q of the system plus Q of the surroundings equals 0. And again, what we're seeing in this right-hand picture is essentially what we do in calorimetry. So what if we wanted to know how much heat energy is moving from the block of iron to the water? Well, we would use calorimetry. The calorimetry is the precise measurement of heat energy flowing into or out of a system during chemical reactions or physical processes. So we know that heat transfer is happening when we place the block of iron into this water, but we don't know how much heat energy is being released or moved around in that system. And so we use calorimetry to help us measure that. The process of calorimetry utilizes a tool called a calorimeter, which is an insulated container that is used to measure heat transfer. There are two types of calorimeters. There's a bomb calorimeter and a coffee cup calorimeter. Both of these calorimeters function the same way and are built with the same basic structure. They both have insulated containers that can be filled with liquid. They contain a thermometer and a stirrer. The container does need to be insulated, though, in order to limit heat transfer between the liquid in the chamber and the air in the surroundings. This actually makes sense. If we're trying to figure out how much heat energy is being transferred between the block of iron and water, we don't want any of that energy to escape into the environment where we can't measure it. So we have to use something insulated that keeps all of the energy inside the calorimeter so we can control and measure the amount of heat being moved around. There are two methods that we can perform, to perform a calorimetry experiment. We could measure the heat energy of a solid substance, or we could measure the heat energy of a chemical reaction. So if we were to measure the heat energy of a solid substance, it's going to look very similar to what we see here in the GIF. First, the chamber of the calorimeter is filled with a liquid that we know of. So typically water is used because we already know the specific heat of water. And then we take its initial temperature. We also know the mass of water that we are using. Then we take an unknown solid with a certain mass and we heat it up so that it has a bunch of energy that could potentially transfer. We're going to take that mass and we are going to place it in the calorimeter. Now, as you can see in this picture, we know that the energy from the iron is going to be transferring to the water. So the heat energy of the solid will transfer into the water, which will raise the water's temperature. Eventually, the system and the surroundings are going to reach what's called thermal equilibrium. And this just means that the exchange of heat energy is equal between the system and the surroundings. This is also the point of time when the final temperature of the system and the surroundings are exactly the same. We can use this information to help us calculate the specific heat of this metal and eventually use the specific heat to help us identify that metal. If we were to do the same process but for a chemical reaction, we're not using solids, so it looks a little bit different. Consider a reaction taking place between two aqueous reactants inside a calorimeter. The dissolved reactants of a certain mass are dumped into separate containers and their initial temperatures are taken first. Then they are mixed inside the calorimeter and stirred until the reaction is complete, which is then when we record the final temperature. Again, this information can be used to calculate the specific heat of the reactants that we used at the beginning of the experiment. So, if the temperature of the surroundings increases during the calorimetry experiment, the reaction is exothermic. This means that heat was released, or a negative Q, by the system into the surrounding water. So water would have a positive Q. An endothermic reaction absorbs heat from the surrounding water. So the temperature of the water would decrease as heat leaves the surroundings to enter the system, which would then have a positive Q value. Now, I will say there are some really wonderful calorimetry videos on the internet. I went ahead and posted them on my playlist on YouTube, so feel free to watch them. Hank Green is always a personal favorite of mine, though he goes a little bit fast, so I would slow down the playback speed to about 0.75 of what you would normally listen to. And then this year, I like to call him Chemistry Jesus because this guy's amazing, but also look, this guy does a really nice job of simplifying what happens in a calorimetry experiment and what we can do to calculate certain values of substances during calorimetry.